this is a school and the conference on networks that usually periodically happens every year, and it is the first time that it will take place in Latin America, in Buenos Aires. So I invite you to apply for it. Unfortunately, the deadline for application is very soon. It is on October 28th. But the good thing that you don't have to send a paper, a complete paper. It's just an abstract. It's an extended abstract. So I invite you to look at what you need, at the specifications for the extended abstract. And you can find all the information that you want to see about the speakers. There are already, we already know who will be the invited speakers for this conference. And we are preparing the professors. We are still looking for some professors. Some are already known for the school that will be giving the lectures for this event. So, but this is a very good opportunity for Latin America. So what I will be talking today is about, I will finish the characterization of the labor network that I started yesterday, and I will focus on something that is called the network reduction techniques, which are specifically chosen for the labor networks. And then I will speak about some temporal analysis that we did for our annual networks. So what I showed yesterday, so I have to go up. I showed yesterday that we obtained, this is what the predominant year-to-year structure of our labor network. Why it is predominant? Because I have 24 periods. No, I have 24 different structures for different representations of my labor mobility network structure. And this is how it looks, the predominant structure, because then I have some kind of transitions, because it has to do with some economic crisis periods, yes, and we will see this. So, and then I show that, for example, what are the standard metrics about this the structure, that I have about a little bit less than 300 sectors, and that this network is not sparse, but it has it's quite dense, and on average, each node has about 200 average degree with the other sectors. And it has a single large connected component. It's quite reciprocal with respect to how many switches are to one direction, and it quite reciprocal to how many switches receives from this sector to back. It has a very high clustering coefficient, and it has short passes degrees. So from this matrix, we saw yesterday that it says it has a small properties, yes? So these are the sectors, and these are the two representations that are usually used to analyze the networks. So that's what we saw yesterday. And we saw, for example, that if I look at this kind of representations for my network, I don't see, apart from these metrics that give me some kind of global characteristics about the topology, that give me what kind of distributions, of degree distribution has this network. And I can see that it has the small world properties, yes, and what is the density of my network, and what is the density per node. I cannot see about the structure so much. So what would be the other representation I have to look? And this, what I said, I have to look at the heat maps. What are the heat maps? Well, this is just the same network. It's a little bit, I put it much larger in order that you can see what kind of sectors are inside this big giant component. So you can see that, for example, the green one, this is this huge manufacture sector. And this is what we discussed on the first class when I said that if I discuss it at the very small granularity level, when we spoke about the different level of details of the data that would be available to me, at the first level of of the availability of the data, this would be a very small network in terms of nodes, and I will show it a little bit further. And when I start going much more in details, this sector will be expanded in about 130 sectors. So that's why I have so many green points here. And in fact, you can see what are in the nodes that are mostly connected in the giant component. And the heat maps are nothing but this structure. If I order from the transition matrix in the alphabetic order, which will be the lexicographic heat map, I don't see any structure. This would be just an alphabetic order that I put my nodes, which will be my sectors. I don't see any structure. But then if I use the hierarchical clustering, which is the typical clustering, you can use the simple linkages or complete linkages to use the similarity distances in order to see and reorganize the transition matrix into the group of nodes and to see how they interact between themselves in order to really emphasize all these blocks that have the greater intensities and to see how the group of nodes interact with each other and with an entire network. So you can see this, really the structure of the network under the consideration. You can see the core that has a very high connectivity, and then you have a periphery that has a much lower connectivity. And this structure really are the ones that will give me much more information about what happens in the interconnected network of my labor mobility, and that's where I will be looking at, okay? And these are done with the dendrograms, because these are what are organizing my sectors in these blocks and these groups that I'm looking for. Yeah?
What is the name of this kind of heat maps?
This is a typical heat map that is organized with hierarchical clustering.
Okay.
This is, that's how it's called.
Okay.
So this is what I said already. So we also you can also, when you analyze this kind of networks, which is a direct flow network, it's just the network of nodes where the links are flows. Of course, apart from the standard measures, you can also analyze the centrality measures, yes, with respect to the nodes, because I can also ask, what is the importance of my sectors of the nodes with respect to the others? What would be those centrality measures? Yes?
Tell us which matrix you can use to analyze the network.
What matrix I can use, what?
To analyze the network, the network. And this map can tell us something about which matrix we can use to analyze the network.
I'm sorry, I probably don't understand. This heat map comes from the matrix of the transitions. Yes, do you remember the matrix that what I showed, that there were the sectors, and then there were the colors red and blue, where I showed that sectors are the nodes, and then the colors they were the flows, where I showed that I put it, how many from sector 1 to sector 2, they were the flows. It's a weighted matrix of transitions. So this matrix of transitions, I organize using the clustering to see the intensity of transitions between the sectors, and I receive this using the clustering, okay? So because these are the dendrograms, if I put the zoom, yes, I put like a zoom on each. I can look here, what are the sectors? What are the sectors that are here, yes? And what are the sectors that constitute this periphery? Do you understand? Okay. in any case, then we can see much more about how to analyze this. Because, of course, you can directly analyze. These are not communities. These are just clustering that comes from the analysis of from the direct analysis of the transition matrices. Okay? Then you can do some community analysis that I will show you tomorrow, not tomorrow, Friday. Okay? Because then you have to ask another algorithm based on a certain criterion to build the communities. Okay? This is just a simple clustering to see, based on the intensity of flows, yes, that they organize in a certain groups. Okay? So which are the centrality measures that you can look at this network of flows? Of course, this is the degree. You can look at the closeness. What is the closeness? Now I pass it quickly because I already know that most of you are working with networks. Closeness is what, if it's not so important to have many direct friends, yes, or be between, but one still wants to be in the middle of the things, yes? So closeness is based on the length of the average shortest path between the vertex and all vertices in the graph. And I will show you now how you calculate it. And you can also look, closeness, you look at the nodes, okay? But then I also said that you can look at the links. So, and then you can look at the betweenness. How many pairs of individuals would have to go through you in order to reach one another in the minimum number of hops, okay? So these are the other ones that you can look at. Of course, you can look at the page rank, you can look at the eigenvalues, and so on. So for example, if you look at the degree centrality, is just, in social networks, it's a very natural measure. So how many connected nodes are on average? This is just nothing more. Is what we usually do is just the connectivity, yes? So this is the mathematical representation. Another mathematical representation, how we calculate the average degree of, or degree centrality of each node. And then the closeness is how close is to the other nodes. So, as I said, closeness is based on the length of the average shortest path between the vertex and all the vertices of the nodes. So, how do I do it? I have to sum the distances from the node to all other nodes. And if the distances are short on average, their sum is a small number, and we say that the node has this centrality. So, I have this close centrality, and I basically is the inverse, yes, of the distances. So you calculate it like this. So if I have, for example, the closeness of a node of an undirected graph, you calculate it like this. So where the SAI is the distance sum calculated from the shortest passes distances, yes? And then you have a differences between the direct network or an indirect node. For example, if you take this example, just to show you, because my network is much larger. So I have this network, yes? So I have 10 nodes. So I have a matrix of 10 nodes. So I have to, pardon. I am implementing simply this formula to calculate the closeness of each node, okay? This is the number of the nodes and the sum of all the shortest passes. So from each node, I have to calculate, for example, from the node to 1 to 3, 1 to 4, 1 to 5, 1 to 6, okay? I have to calculate the shortest path, picking 2 nodes in the network. Do you understand? And then I put what is the shortest path and what is the sum, calculate the sum of the shortest path, and then for node 1, what would be the closeness of the node 1, okay? So this is just the distance matrix, and then I calculate the closeness for each node using this distance matrix, okay? That's how you calculate it. So, and this would be the full vector of closeness centralities for each node of this graph. So then, on the basis of this, I can see that if this is node 1, 2, 3, 4, I can see that the node 4 has the closeness centrality, okay? So sorry, how do you calculate betweenness? You have to see which is the node more central based on the diffusion process. So you calculate nothing more than how many, the number of shortest passes that will connect. If you are interested in the betweenness of the node I, you would see how many shortest passes connect any nodes J, I, K, but that will pass through node of the interest. Yes? So I will pick the node I, and I will pick any node J. I calculate all the possible shortest passes that go from I and J, but I'm interested among all the shortest passes from I to J, how many of those pass through the node K. Well, acá I made another example. You pick the J and you pick the K. These are the two nodes. So I fix how many shortest passes are between the J and K. This is my term here below. And then, since I want to know the betweenness of the node I, among all these shortest passes, I want to see how many of those pass through the node I. And this will give me, this relation will give me the betweenness of the node I. Okay? So these are the other centrality measures that might be very interesting for the analysis. Okay? And these are also were applied for the network. But let me not stop here, because I'm much more interested to show you some other things that were found and very interested for this particular network, because as I said, we had 24 networks, because we are analyzing the period of 1996 to 2020. So what I am showing here, this is just the evolution of the transitions, yes, along all these years.
So this is the flow of pairs on people?
Yes, these are the,
okay.
yeah, these are the transitions. So you can see, actually what I'm interested in is only this red line. Why? Because I only analyze inter-industry transitions, okay? So I don't look at this diagonal in the matrix. So for the moment, I'm not analyzing that. So if I would have been economist, yes, and I look at this evolution, what I would see is that clearly, and that's what an economist did when I showed him this, he said, you have 4 periods here. That was his answer. Myself, I see much more than 4 periods here, okay? Because, of course, I have some inflection points here. But economists said, no, you have 4 periods here. You have a period of convertibility, and so he put me 96 to 2002 all together. Sorry. You have post-convertibility, and he put from 2003 to 2010 all together, local stagnation, and recession. So what do you observe here? For example, here in this period, 2001 is inside. And this is a huge crisis in Argentina. But for him, this year is nothing special in terms of the data. Of course, if he analyzes it as a special economic period, there are lots of things to be said. And they are analyzing it very specifically. But for this example, he just put it over there. 2008, it's another international crisis, and it's again inside. What does it mean? It means that if I make an average, it's just achatar? Flats. Thanks. It flattens all the years. So I don't see the specificity of 2001, isn't it? So that's the problem, okay? And when we speak and work with economists, that's how they do. Because then this work has been done with people from Ministry of Ministerio de Trabajo, of Labor. And so what they want to analyze here is that they don't want to go year by year. They just said, no, let's work with averages, because for them it's just the representative year. And we say that there is no representative year. You have to take away from here certain window. Okay, that was all the discussion, for example, and of course we were able to show that. So, but let me show you something. So this was, I picked 4 examples from different periods, no? And these are the, let's say, predominant structure for each period, yes? So I picked up, this is 2005, this is the structure of the network that I was showing before. This is the structure of the network for 2015, this is for 2001, and this is for 1997. If you look at this, what can you tell me? They are almost the same. Yes? You cannot extract a lot of information, but truly you can say that they preserve very similar characteristics, that they all of them, all these 4, they have this tendency to demonstrate the giant component, yes? All of them have the same small world properties. They have the same, very similar, except this one, characteristics with respect to the clustering and so on, okay? Let me show you the heat maps. And these are where the very interesting things happen. And this kind of representations, they are not very friendly to work with. When I say they are not, I refer to the economists, because for them were very interesting to find out that they can obtain a lot of interesting and fruitful information. And what do we observe here is, yes?
Do you always keep the same variables?
Yes.
Or you're not moving the variables around?
No.
From one to the other?
No.
So what means is that according to different ways in which the economy goes, it goes the linking between different companies.
Yes.
Let's say.
Yes. They reorganize.
They
yes.
reorganize it.
Exactly. Yes.
No, I'm trying to understand.
Yes. Yes. So what you have here, that the number of sectors is always the same. What is different is reorganizations in each case, and it has to do with the period under the consideration. Yes. So for example, here, let's see, 1997. You can see the core-periphery structure. Yes. And you can see that there are, in fact, you can always vinculate with the period where this data comes from. So here you can see that you observe a very strong core, and then you have almost 2 peripheries. Yes. Then you can analyze what kind of structure and interconnections you have here. In 2001, you don't have any structure at all, because there was no activity at all. So there was no transitions, almost nothing. So the system was disorganized, and that's what it shows you. Not even here it finished to show you the strong core, okay? This is what we already showed, and here, so these differences between the core-periphery structure, what it demonstrates you is how, from period to period, the reorganizations between the sectors is changing. And that's how it reflects in the size of the core and in the size of the periphery, okay? So this was a very interesting information. So this slide, I will go back afterwards because it was interesting afterwards to see what else can we do with that, okay, to compare. But this was like the first information. But how much time I have?
15,
okay,
15 minutes.
15? Okay, then I want to show you one other technique, and then I come back to this one. But this, I worked with network flows, with flows which are direct flows between the two sectors. But then I want to ask you, is there any other network that I can extract from this data? Do you remember that in the first class I said, individuals, when they change jobs, they don't change jobs just because they decided. It's like, I decided not to have a link of friendship with some of you because I'm angry. No, there is a reason for that. It's like there is a reason why one sector has a demand for certain individuals, for certain capabilities, okay? So here, there are capabilities and knowledge exchange between industries. And there is what is called skill relatedness. And while individuals are working in one sector, what are they doing? They are capacitating. So they are getting much richer in their skill relatedness, yes? So this is a very important thing as well, and we can do something about that. So we can describe how strongly the industries are connected through labor flow. We can see how they reflect similarities in the industries and human capital requirements. And here, there are two nice papers, and I invite you to look at it. That first, we can see, can we extract what is called industry space? Okay? And there is an analogy, what is called product space. I don't know who is familiar with product space here? Good. Product space comes from the notion that when the countries are exporting products. So there is this huge group in Harvard, and they started also in MIT with Ricardo Hausmann, with Cesar Hidalgo, that developed what is called the Atlas of Economic Complexity. So here I left you the link. So if you go here, for example, you can go and explore. It is very useful for investigation. So you can go to Explorer and use the data. They have a data which is available. So they have a data that is processed for any country. You can download it. And it is already, it's not in a raw format. It is already processed and cleaned. And you can use it for investigation. So you can, for example, choose the country, and you can see how much exports per year, because you have the time scale, you have per product. So it's a huge database. It's like an economic observatory, okay? But let me go back here. So what they did, they built this network, which is the product network. So you have the nodes, which are the countries, and they are vinculated with each other via the products that they export in common, okay? Because it's like they have the proximity. O sea, let's say that there is an indicator that is developed that if Argentina and Brazil are exporting some products in common, what is the proximity, how much they are close in exporting these products. So this link will be weighted by this proximity indicator. And that's how they can build this network, which is like a product network. So this is like showing all this export-import activity of each country at the regional level, at the world level. So this is a very interesting work. And the same thing we can think about too in terms of the labor and skills. There is another work that is very interesting, which is done by Dominic Hartmann. He's now he's a German guy who is now working in Brazil, in Universidad de Catalunya. He together with others, he applied the same concept, but to map. It's like he did mapping stratification. He did is industry occupation space to study the network structure of inequality. It's a fantastic work. And for example, this is how the network is look like for the Brazilian industry occupation space. Brazil has a lot of interesting data, for example, to study. Argentina doesn't have all this data. So, for example, Argentina doesn't have occupations. So we cannot do this kind of details. And
Doesn't have what?
occupations.
Occupation.
Here, for example, this network is for industry occupation space. So, because Brazil does have occupation information. In Argentina, we would like to do this kind of network, but we don't have information about occupations. You can get these occupations if you analyze the survey IPH. It's about that is mentally done, but this is not like a very clean data. You have a lot of noise. So each node here, it's like represents occupations and is colored. It's like the community. So what you have here is like how many occupations appear in different industries. So you don't only have how the industries interact with each other, but also what kind of occupations they concentrated in each industries. Okay, so it's a very interesting work, and I leave you. So if you click here, you have the paper with all the details. Okay, so I leave you the link as well. So the same thing we have. We started to think if we can do something very similar for our labor network. Okay. So if we can build what is called industry space, and if we can find what would be the industry space for our Argentinian formal private labor network. I again tell you that it's not represented network because we only work with a very small segment of data. At the same time, what I'm showing, it is like a certain reduction technique of my global network, okay? So from my flow network, from my original network, what I am looking is like I am applying one of the possibilities of the reduction techniques to see how I extract a certain information. So I am reducing my network in order to obtain what is called the industry space. And the idea of this reduction technique is based on the skill relatedness, on this, that the flows, that these job switches between these two nodes on the network have to do with the fact that there is this relatedness between the nodes. So the idea would be, what is the indicator, what would be the indicator that manifests this relatedness, okay? And this is based on the paper by Nefke in 2017. Here you will find this paper, it's available. So this link does not, all my links, they don't only show you the references, they have the references. So they're already there. So what it shows is that there are mobility costs associated with specificities. So firms, industry tasks, in the accumulation of worker human capital. Labor flows, they reveal degree to which human capital moves between industries. In fact, this, I will explain you this. It shows, it's like if you find, it's like the divergence between the observed flows, which is my transition matrix, where the one that I showed at the beginning, where the individuals go from no individuals, the flows that I observe from one sector to another, with what would be the expected flows. It's like similar to, this would be like when you work with the contingency tables, okay? So this is my matrix. These are the observed flows in the matrix. This is what I have here, see? And I would calculate what would be the expected value of this matrix, yes? This is the way I calculate the expected value of the matrix. This is just the mathematical representations. If you want to have more details about how to implement the methods, I am available afterwards. But since I have a little time, I want to show you results. And then there is a sort of normalization because I don't want to have exceeded flows. So they are normalized. And then this is the way.
This is what is called an embedding of the graph, or not?
No.
Okay.
No. And then I get what is called the skill-related net matrix. And then with this is just the documentation. So I put you the explanation how to isolate the structure that underlines inter-industry flows. So how we calculate the observed volume values with respect to if the work is switched with probabilities proportional to how to calculate the expected value. And this is how I construct the industry space. So I pass from the observed, from what I have, my data. I calculate the matrix that would be the skill-related net matrix. And then I extract my industry space. But to extract my industry space, I have to do what is called maximum spanning tree. This is the opposite of the minimum spanning tree. If you know what is minimum spanning tree, is when you want to connect all the nodes in your network with the minimum possible number of edges. This would be the minimum spanning tree algorithm. In this case, I don't want to do that. I'm not minimizing that. What I want to do the maximum spanning tree. And this would be as if I want to get the network with the maximum possible weight. Why do I do that? Because I want to get the maximum flow. Because I'm interested in the labor flow. So I am trying to reduce my network, my original network, without losing what is called the total, ¿cómo lo digo? The information about how much labor information it absorbs. Okay, so I want to leave my reduced version of the network with these links that contain as much information about job switches as possible. You understand? And this is what is done with the maximum spanning tree. It's an algorithm. For example, there are two different algorithms. One of them that we used is by Prim. And this would be the red that you analyze. And this is like an industrial space. So it contains information about the industrial space. And how do you, how do you analyze it? You do the core-periphery decomposition. Because now what I'm interested is the relationship between the industries. Because I only have the information about the industry space. Es el espacio de industrias. Okay, so now I want to look what happens with this industry space. So I look, what are the industries that are much more connected, less connected? What is the connection between these different blocks and so on? So I can apply the core decomposition, core-periphery decomposition. I can decompose this network to reveal the structure. So I can accomplish it by iteratively filtering of low-degree networks and focusing on the remaining, which are much more dense and dense cores. You follow me? Okay. So the degree of each node can be used to separate a network into distinct portions. And I will have the ones that are very dense, they will give me a core. The ones that are low degree will give me the periphery, and so on. So this is the algorithm how you do that. And that's why what I will be looking is I will start with the low degree K, and then I will getting K minus 1 core, because I want to have how many core degrees, because I'm doing the core decomposition, has my industry space, okay? And what I have is this. So I have, my results show that my industrial space for this network is spanned in 6 subgraphs, yes? And for example, the K core is, has 191 economic activities, yes? And it is connected with at least 6 and at most 31 other sectors, okay? And what does it have? And this core, this K core, absorbs about 72% percentage of employment, okay? So it is, what does it say? It is the most, it's a huge one, okay? And it is spanned about in 17 big divisions of classifications. So then if I want to have details, and I have details, but I didn't bring them, I can leave and look at them. Who are they, okay? So, and then I see, for example, who are in the periphery, yes? And in the periphery, I have these 2 cores, 1 and 2, which are together have only 59 sectors, yes? And these are clearly a periphery. And in total between them, they only have 2% of total employment. So this is a very interesting way of analyzing. So I could build an industry space. So on one side, I can analyze directly the flows, because this is the information that I have. But then I can get a little bit more precisely the information based on relationship between the industries. So, and this is the thing that I wanted to show you. For example, I almost don't have time. But for example, if I look for different periods, so here from this period, and from this period, and the core of maximum connectivity, and you can see how, what are the sectors and how are you can see that, in fact, the sector, pardon, está en castellano, that the sector of mayor connectivity, they basically belong to sector of manufacture, which is what we were observing here. There is another reduction technique as well, because I can also work directly with my flow network, but I will show you that tomorrow, because I'm run out of time. But let me show you, and this also I will show you tomorrow. But let me leave you one thing that I prepared. So because otherwise it seems that I don't leave exercises. So one thing that we already were doing, so it's fine, is 1. But then the 2, since Marcelo is not here, he's giving a class now. He was doing a prisoner's dilemma game the other day. Do you remember? So I suggest you that you place a prisoner's dilemma game on a spatial structure. So because when the prisoner's dilemma game, in fact, it's a very interesting game, because it poses problem of coordination, of cooperation. And cooperation never occurs in game theory. So, and the natural selection always says that to defect is a strategy that always appears. So there are a lot of people that dedicated their time to study how cooperation appears and what to do to help cooperation to appear. So this game has been studied a lot on regular lattices, and there is a lot of works done by Novak and May. They are published. For example, there is a paper in 1992, 1995, when they that is Nature, that they put this game on a lattice, and they showed that using an imitation, going back to the video that Pablo showed to you in the morning, and placing this game on a lattice, yes, where you have only 4 neighbors, and even if you have 8, these are 2 standard neighborhoods in game theory, you can obtain almost 33% of cooperation. And so there are lots of different works afterwards that have been done, starting to complicate spatial structures, yes, with imitation dynamics. And they were showing that scale-free favors cooperation, that small worlds favors cooperation, and so on. But the challenge would be here is that, in fact, what really changes the cooperation is the rule. So whenever you change the imitation rule, that's when it does not work. Whatever spatial structure you try. So I invite you try to this desafío challenge. What other updating rule you can try to implement without going to very complicated spatial structures, and see what happens. And then I told you that I will leave you 2 papers on the financial networks in case you want to try to work a little bit with financial networks. These are very interesting, simple models, and try to simulate them, or at least to understand them. So these are very simple, comprehensive, and accessible. So with this, I will stop. Thank you very much.